Welcome back to the deep dive where we dig into the hardest research papers out there and pull out the insights you can actually use.
And today, we are going after what you could call the three white whales of modern AI.
Exactly. I mean, for all the amazing things large language models can do, write poetry, code an app,
hmm
they still have these three sort of deep structural weaknesses. And those are the things holding back true mission-critical adoption.
That's our whole mission for this deep dive. We've got three huge problems, and we found three really cutting-edge solutions.
Well, let's lay them out. First, there's the big one, the trust problem. It's the fact you can't guarantee accuracy, the whole hallucination issue.
Or, to be more technical, the model's inherent stochasticity. It's probabilistic.
Right. And you just can't bet $1 million legal contract or a patient's health on a probability.
Then you have the second problem, scale and speed. We're basically hitting a wall, a physical wall with digital silicon.
The energy consumption is massive. And there's a hard limit on how fast and dense you can make a chip before physics just says no.
And finally, the problem that I think everyone who's used these models has felt, context and memory.
The memory window. It's fixed, it's short-term. They can't hold an entire book in their head at once, which really limits deep understanding.
But these aren't permanent problems. That's the key takeaway today. We're going to walk you through three specific breakthroughs in reliability, in hardware, and in architecture that are actually solving these things.
Okay, let's unpack this. And let's start with the one that really matters for regulated industries, solving trust. We need proof, not just, a plausible sounding answer.
Exactly. I mean, once you're in finance, legal, healthcare, a 95% correct answer is a 5% liability. That stochastic nature is a total non-starter, legally.
So that's why researchers are chasing this new metric. It's called soundness.
Right. Soundness is all about minimizing false positives. The math is simple. It's 1 minus p, where p is the probability of the system making an incorrect claim.
And the goal they're shooting for is 2 nines.
2 nines, 99% soundness. That means a near zero chance of the AI telling you something is true when it's actually false.
So how do you get there?
Yeah.
It seems like you can't do it with a purely neural network.
You can't. You have to move into this hybrid world of neurosymbolic AI. And the framework we're looking at is called ARC, or Automated Reasoning Checks.
Okay, neurosymbolic. So you've got the neural part and the symbolic part, a marriage of two ideas.
A perfect marriage. It uses the neural net for what it's good at understanding natural language, but then it uses the rigor of formal mathematical logic to verify the output.
I have to ask, why not just use something simpler, like RA?
Yeah.
Retrieval augmented generation. Just pull the facts from a database.
Because RA pulls facts, but it doesn't prove the logical consistency of how those facts are applied. ARC provides an actual layer of proof. It has two main stages, and the first one, the policy model creator, or PMC, is absolutely crucial, and it all happens offline.
So that this is the prep work. The PMC takes something messy, like a 100-page corporate policy document.
Or an insurance policy, right, all that fine print.
And it translates that natural language into a formal machine-readable logic. I see they use SMT-lib rules and schema.
And here's the really valuable step. The process has this optional but critical step. Human vetting.
So a real person, a domain expert, looks at the translated rules.
Exactly. And they can spot ambiguities or even contradictions that were hiding in the original document all along. It's a bit of an upfront cost, but once that formal model is vetted and approved, it becomes the single source of truth. It's unambiguous.
Okay, so you've built your bulletproof policy model. Then what? The system goes live.
And that's when the real-time guardrail kicks in. The answer verifier, or AV, this is what watches the live conversation, the user's question, and the LLM's proposed answer, and translates that into logic.
Now, you said this is where it gets really interesting.
It is. To hit that near-perfect soundness, the AV does something called redundant translation. It doesn't just use one LLM.
It uses more than one.
It runs the same question and answer through multiple LLMs simultaneously.
Wow, so it's like getting a second opinion and a third and a fourth all at the same time.
Precisely. And even if they all phrase the logical output a little differently, the symbolic reasoning engine at the core can check if they are all semantically identical.
I see. So if 3 different models agree on the core logic, you can be incredibly confident it's right.
You move from likelihood to mathematical verification. That's the leap.
And the results, they hit the target.
It exceeded it. They achieved 99.2% soundness. But the feedback it gives is just as important. It's not just a true or false.
Okay, let's use their park admission example. A user asks if their $35.40 is enough for a senior ticket in low season. The LLM might say, no, it's not enough.
Right. A normal chatbot would just stop there. But the ARC system's verifier comes back with a finding of satisfiable.
Which is a formal logic term. What does that actually mean for me, the user?
It means the LLM's answer isn't wrong, but it's not the whole truth. It's consistent with the policy, but not necessarily true. The AV found a loophole.
And it tells you the loophole.
It provides a detailed counterexample. It shows that, look, if the visitor uses $15 of their loyalty credits, which the policy allows, their final cost drops below the $35.40 limit.
So it's saying, hey, your chatbot wasn't lying, but it was lazy. It missed this other valid path.
Exactly that. It flags the answer as incomplete and provides the auditable, logical proof. That's what a company can take to a regulator. And remember, that human vetting step. In one study, it pushed soundness to a perfect 100%. We're talking about verifiable AI.
Okay, so we've solved the trust problem. We have verifiable logic. But if that proof takes an hour to compute, it's not very useful.
Which leads us straight into the next bottleneck, the speed and depth problem.
We're moving from software to the hardware itself.
Right, we're hitting physical limits. The energy these huge digital networks consume is just unsustainable. So the research is pointing towards optical neural networks, or ONNs, using light instead of electricity.
Light is faster, it's more efficient, it sounds perfect. So why aren't we all using them already?
Because of the depth wall. Photonics is an analog process. So with every single layer the light passes through, tiny errors creep in and they compound.
Like a snowball rolling downhill.
Exactly. So historically, ONNs just maxed out. They couldn't get past about 10 layers, which is way too shallow for the deep learning models we need today.
And that's what makes this next paper so incredible. The breakthrough is a device called the SLIM chip. That's single-layer photonic computing.
SLIM is brilliant. It solved that error accumulation problem by doing something completely counterintuitive.
Okay.
They introduced controlled perturbative noise on the chip itself.
Wait, hold on. You're telling me if the system has an error problem, their solution is to add more noise.
It sounds completely backwards, I know, but it's not random noise. It's a very specific mathematical perturbation.
Yeah.
And that noise, it decouples the computational correlations in the system.
And what does that do?
It lets the chip perform the massive calculations of a deep network using only a single physical layer of light propagation. You get the computational depth of hundreds of layers without the physical errors of light passing through hundreds of layers.
That's incredible. So it sidesteps the whole error accumulation problem. But what about the errors that do happen?
They guarantee a bounded error rate. They have a detection-based activation function, which is kind of like a little cleanup crew. If a light signal gets distorted, the system immediately snaps it back to the nearest correct signal level. So the errors are contained, they can't spread.
The scale this opens up is just, it's mind-boggling. You're saying it shatters that old 10-layer limit?
Completely. They've demonstrated deep ONNs with over 100 layers. And in their tests, the error rates stayed flat across more than 200 layers.
And this isn't just theory, right? They ran this at high speed.
Yep. At a very real-world data rate of 10 gigahertz.
So what did they run on it? Did they build actual LLMs?
They did. They ran a 100-layer network for image classification and got 85.4% accuracy, which is right on par with an ideal digital simulation. And yes, they built real LLMs, one with 384 layers for text generation and another with 640 layers for image generation. The performance was nearly identical to a digital system.
The fact that it's a single-layer approach must have other implications, too, for, like, the physical layout.
Huge implications. Because the real work is in that single layer, the computational depth is no longer on the chip itself. It's in the chip-to-chip connections.
So you're not limited by one tiny piece of silicon.
Not at all. You can move to 3D clusters of these chips connected by light spanning hundreds of meters. We're talking about designing supercomputers as distributed clusters, paving the way for ZettaOPS.
Zetta what?
ZettaOPS.
Right.
That's 10 to the power of 21 operations per second.
I can't even picture that number. So we have solved trust with logic and speed with light. That leaves the final big hurdle, the model's own cognitive limit, the memory problem.
The memory problem. Yeah, this all comes from the transformer architecture's attention mechanism. The cost, the computation, it scales quadratically with the length of the input.
Meaning if you double the document size, you quadruple the cost and the time.
Exactly. It's unsustainable. It's why models can't just read 10,000 pages and have it all in their immediate context window.
So what's the solution here? I see we're looking at two things, the Titans architecture and the MIRAS framework.
Right. Titans is the tool and MIRAS is the blueprint. And they try to get the best of both worlds. the speed of older RNNs with the power of modern transformers.
So how does Titans attack the memory issue?
It creates a dedicated long-term memory module that is itself a deep neural network, a multi-layer perceptron. So the memory isn't just a simple vector, it's its own little brain, a highly expressive summary engine.
So it's not storing words, it's storing compressed concepts in a separate module.
You got it. And the most ingenious part is how it decides what to remember. It uses something they call a surprise metric.
The surprise metric. So it just remembers the weird stuff.
In a way, yes. But it's very efficient. As the model is processing data, if it encounters something really anomalous or unexpected.
Like a banana peel showing up in a financial report.
Exactly. The model's internal error signal, the gradient spikes. It has a moment of confusion.
And that spike, that's the surprise metric.
That's the signal. The model says, whoa, this is new, this breaks the pattern, I need to store this in long-term memory. It's selective. It avoids wasting space on redundant info.
How does it manage that memory over time, though? It can't be infinite.
It has two smart tools. One is momentum, so when it stores that surprising banana peel token, it also grabs the next few tokens related to it. And the other is an adaptive forgetting gate, which is a decay mechanism that slowly prunes away information that becomes less relevant over time.
Okay, so Titans is the implementation. What about MIRAS? What does the framework give us?
MIRAS is the unified theory. It basically says all these different models, transformers, RNNs, Mamba, they're all just different types of associative memory. And it defines the 4 key design choices you can make for how a model remembers things.
So it's like a cookbook for developers.
It is. It lets them move beyond just using simple metrics like mean squared error, which can be thrown off by outliers. A MIRAS-based model called YAD, for example, uses something called Huber loss. It's much more robust to messy, real-world data.
And the performance benchmarks seem to back this up.
They do, especially on the Babylon benchmark. This is a test of reasoning over extremely long documents.
And how did Titans do?
It excelled at extreme long context recall. Even though it's much smaller than something like GPT-4, it actually outperformed it on these long context tasks. It successfully scaled its context window to over 2 million tokens.
2 million tokens. Just to put that in perspective for you, that's not just reading a document. That is instantly digesting and reasoning across 10,000 pages of text without forgetting what was on page 1.
It changes everything for fields like law or complex research.
It really does.
Ew.
So we've seen 3 absolutely fundamental breakthroughs today.
They really are, and they fit together so well.
There's the logic from ARC, which gives us that guaranteed auditable proof. Then there's the light from SLIM, promising this zeta-scale speed and infinite depth. And finally, long memory from Titans and MIRAS, pushing context to millions of tokens.
These aren't just small tweaks. These are direct solutions to the biggest roadblocks: unreliability, physical limits, and cognitive bottlenecks that have held AI back for years.
Absolutely. So let's leave you with a final thought. Consider the impact when a chatbot for your company's internal policies gives you an answer that isn't just plausible, but is mathematically proven to be 99.2% sound. And that answer is computed instantly on a kilometer-wide optical computer cluster that can reference and reason across the entire history of your company's legal documents. That fusion of proof, speed, and memory, it's the future these papers are building right now.